Hey everyone, in this second video of Lecture 11 we're going to be looking a bit more at the D block, some more coordination chemistry and one of the exciting new research topics of the last 20-ish years, which is metal organic frameworks. We're then going to be looking at how, as before, they can tackle some of the societal problems. So let's pick up where we left off with coordination chemistry first to understand a bit where they come from. So we saw before how ligands such as oxygen or the cyano ligand in this case can coordinate to a metal center. But we really just focused on one metal centers, so like a nickel with 6 waters around it or something. But it doesn't just have to be one metal center. So we've talked a bit about the dichromate anion, but haven't really looked at how it's formed. And this is a coordination complex ion. But this time it's got 2 chromium centers. They're both tetrahedrally arranged, but one of them, one of the oxygens, is bridging across both of them. So the O2- ligand is a ligand that can act as a bridging ligand, so it can coordinate to 2 metal centers. And an example I've got here, taken from the textbook, is of Prussian blue, which is used as a pigment. It's a blue, quite a nice blue colour. But this happens when you take an iron cyano complex and add an excess of iron 3+ ions. They form this big network where the carbon and the nitrogen of the cyano can coordinate to neighbouring metal centres. So that's the real important thing that we need to know before we get into MOFs, is that ligands don't have to be just stuck to one metal. They can bridge across, and that's really where MOFs come from. So MOFs are made up of 2 parts, and both of them actually can contain bridging ligands. So the first one is what's called a node, and this is a metal center that contains one or more metal atoms, and they're quite often held together by bridging atoms. So I've got an example of one on the left here. So this is a metal node, mainly this bit in the middle here. So the node in this case is Zn4O. And it's this little tetrahedron that's shown down here. So 4 zinc atoms on the corners of a tetrahedron with an oxygen in the middle. And then what's shown in the rest of the picture is some bridging atoms, like bridging across 2 zinc atoms. Now, in this case, the bridging atoms, the bridging ligands across the 2 zinc atoms are just these acetate groups. But you can actually get really long ligands that are double-ended, so they'd sort of have these 2 oxygens on both ends of the ligands, and these are called linkers, because then you can essentially get 2 of these nodes and have one ligand joining them up, and that's what's shown on the right here. So the blue circles are these Zn4O nodes that we've shown here, and the red lines are the linkers. And the linker in this case is a longer one with a benzene ring in the middle. So very similar to this, but then instead of the CH3, there's a benzene ring, and it's symmetrical. Linkers are quite often symmetrical, more often than not. Again, with this sort of carboxylate group on the other end. And then it bridges across and coordinates a lot of these tetrahedral Zn4O nodes together. And it makes what's called a metal organic framework. And the really defining characteristic of these frameworks is that they're really crystalline, because they've got all of this order is super uniform, super periodic. But the main use of them is their porosity. So you can see they've got large holes in them, and you can see it better in this one. Between these, in the red squares, is actually empty space that's very uniform. You can choose the size of it, and you can choose what sort of functionality is on the inside as well. So then you can apply it to absorb gases or catalyze reactions, or do whatever you want. And that actually makes MOFs the kind of connects of chemistry. So like whenever I see MOFs introduced at conferences, old professors are always there saying, oh, MOFs are like Lego. But they clearly didn't play with the toys right or remember the name, because they're much more like Connects than Lego. Because there are such a wide number of these nodes and linkers available that you can get sort of an endless array of MOFs. So this is what I think is a bit more like a Kinect. So you've got all these metal nodes here of different shapes, sizes, colors, whatever. All these different shapes, colors, sizes, and linkers, and you can just tailor make them the materials to what problem you want to solve. And I was reading the other day, I think even the article is a couple of years out of date now. When it was written, there were over 90,000 types of moths that have been synthesized, and they've predicted over 500,000. But as I say, these can be tailor-made. So some of these moths are very similar to each other, just with one little change, and it just makes them better and better at what they do. And here's an example here of how they make them. So you can just take an inorganic building block, is what this BB stands for, such as the ZN40 we just saw on the last page, or this copper one. This is the paddle wheel, is what PDW stands for, nothing chemical, because it looks like a paddle wheel. Combine them with your organic building block, which will be the double-ended linker, or triple-ended in this case, and you can coordinate the two together and get this, these big frameworks that do whatever you want them to do. So now I'm going to show you 3 examples of moths in the recent literature and how they can help us solve some problems. So let's start by looking at the UIO66 family of moths. Now this is called UIO and they've all got funny code names like this because there's no official naming convention when you discover a moth. So UIO stands for University of Oslo, which is where it was first created. And this family bit of it comes because, as I was saying, moths can be really easily tailored to the applications, and there have been lots of changes to the UIO66 moth. So one of the easiest to explain, best example actually, is the moth UIO67 instead of 66. So they've both got exactly the same metal node, which is shown here, these enlarged red dots. And they contain 6 zirconium atoms with bridging oxygens or hydroxides, and hydroxides. The linker for UIO66 is this terephthalic acid, which actually becomes terephthalate. The hydrogen disappears and get a minus charge. And these link between those zirconium 6 nodes. UIO67 has exactly the same linker as this, but it's actually a bit longer and has another benzene ring. So if you'll ignore my appalling drawing, it will be like that instead. So it's just like a bit longer, almost twice as long. And the effect this has is that the pores are then much bigger, because the pores are like the defining feature of the moth. But sometimes, especially if you're doing like liquid phase experiments, the diffusion of the liquid into these really small pores can be really slow and actually hinder the reaction. So if you can make them bigger, the reaction will go quicker. Now this UIO66 family of moths is really important because they're the most promising that are being investigated at the moment for degrading chemical weapons. So although chemical warfare agents and weapons have been banned for decades, there are still loads of examples of chemical weapons being used at the moment, either in political cases like the Russian one that's been in the news recently, or in the Syrian civil war as well. They've actually been using like VX and sarin in cities on civilians, which is horrible because these kill you very quickly and very nastily. So then the research that's been doing at the moment is that how can, if there's a chemical attack, how can we degrade these before they can hurt people? And this UIO66 moth does, and UIO67 actually does an even better job of it. They can catalyze the degradation of these. So the VX or the sarin are quite similar to this molecule here with the phosphorus or the phosphate group. They can go into the moth and they'll be degraded, and they'll just make harmless byproducts like these two. And one of the really big steps forward with the UIO66 is they've actually managed to make clothes with the moth on the fabric, so sort of cotton with the moth on the fibres. And then it's hoped that people in these like high risk areas of chemical warfare can wear the clothes, and when the chemical weapons get released, then the clothes will protect them and actually degrade the chemical weapon rather than them being killed. So these final 2 examples are both looking at how we can solve the climate change problem. And the first one I've got is this ZIF-8 moth. Now this is using zinc N4 tetrahedra. So in this case, there's only one metal in the metal node, and it's got 4 nitrogens around it in a tetrahedral shape, and it's got these 2-methyl imidazole linkers. And now that's actually what ZIF stands for. These are zeolitic imidazolate frameworks, so they've all got imidazole linkers, and there are hundreds of these ZIF type MOFs. Now the figure I've got here is one of my favourites that I've seen in literature. Actually, it's a really good picture, and what they're aiming to do is show that ZIFs can take CO2 out of the atmosphere. So atmospheric CO2 is the real problem of climate change. The concentrations are higher than they've ever been, and without stopping it, climate change may become irreversible. So it's really important we can stop pumping CO2 into the atmosphere. And one of the ways they think we can do this is by putting ZIFs, in this case, or MOFs in general, in places that are emitting CO2, so that the MOF captures all the CO2 instead of it going into the atmosphere. And it seems to work extremely well. So from this paper that I've taken this lovely picture from, they've shown that 1 litre of ZIF 69, which is a slightly different one to ZIF 8, they've just got, again, small changes. 1 litre of the MOF can hold 83 litres of CO2, which is quite a lot. Now, the reason I've taken the nice picture, and the picture is of ZIF 8, is because it shows that when you make these MOFs, they can make quite large crystals, and in this case they've sliced a crystal in half. You can see it's got this wonderful hexagonal shape, and then inside you can actually see all the nodes and the linkers. These like bright things on the corner are the zinc nodes, and then the slightly lighter corners of the hexagon are the linkers going between the nodes. And then if you zoom in even further, you can see this really faint thing in the middle, and you can see them inside all of the pores. And what the people that did this research believe it is that this is actually a molecule of CO2 within the pore of the ZIF 8 structure. So I think that's a really nice microscopy image, but a really good way that we can use MOFs to solve the climate problem. And then again, to sound like a broken record, how can we help make hydrogen as part of the economy? So in this case, I've gone for MOF 117. So not named after anything, it's just a number code for this one. MOF 117 was actually investigated initially for CO2 capture as well, like ZIF 8 that I've just shown. So a lot of these MOFs can capture all sorts of gases, but this one's particularly promising for hydrogen capture as well. So one of the problems we said about putting hydrogen in things like cars is that it's not very energy dense with respect to the volume. So you'd need like a really big storage tank of hydrogen in the car at a really high pressure, which also has obvious safety issues. So what they want to do is use MOFs to store hydrogen at low temperatures, so that when it's heated up, it will release the hydrogen. And in this way, you can store just as much hydrogen in a much smaller space, or have the same space as the tank would take up, but with a lot more hydrogen on board. So it just makes it more feasible to have hydrogen on board of cars. So this MOF 177 is very good at doing this. So it's another zinc-based MOF, and in fact these metal nodes are very similar to the examples I showed taken from the textbook at the beginning. These ZN4O with CO2 ligands, or bridging ligands. So these are the nodes, and then they've got these benzene tribenzoate linkers. So they're sort of a triangle with, I'm going to draw benzene as a circle because I'm lazy. So like this. So you get this triangular sort of arrangement between the nodes. Actually, I didn't notice there's one directly pointed at the screen that's very easy to see. And this can actually store almost 20% of its own weight in hydrogen, and that means a big saving in space, or a lot more hydrogen in the same space on board cars. And it also makes it a lot safer. Like compressed gas is quite explosive, especially when it's hydrogen, whereas a MOF at room pressure will be a lot more safer. So that's the final example how we can use a MOF to solve a problem facing society at the moment.